In this video, I'd like to show an example of solving differential equation by Laplace transforms. Before starting the example, you need to know the following steps to solve differential equation by Laplace transforms. Step 1. Take the Laplace transforms of both sides of the equation. Step 2. Solve for the Laplace of y. Step 3. Manipulate the Laplace transform f of s until it matches one or more table entries. Step 4. Take the inverse of the Laplace transform to find the original function f of t. And we use this Laplace transform table, which consists of 3 columns with 28 entries. Let's begin the example. Solve y double prime minus 4y prime plus 5y equal t, where y of 0 is 1 and y prime of 0 is 2. Step 1. Take the Laplace transforms of each function. For the first Laplace of y double prime, let's take a look at the table to find out the transform. This Laplace transform table consists of 3 columns: transform number, f of t, and Laplace transforms. Since the function is y double prime, we take the entry number 3. We found the Laplace transforms for y double prime in the table, so we replace the first function with it. Move to the next function y prime to find out the Laplace transform in the table. Since the function is y prime, we take the transform number 2. We found the Laplace transform for y prime in the table, so we replace the second function with it. Let's move to the next function, y. Since this is the original function y, we keep it as y. So the Laplace transform y is just Laplace of y. For the right side of the equation, let's find out the transform of t in the table. We can see t function in entry number 6. We take 1 over s squared as the transform. Taking the Laplace transform of t function to get 1 over s squared from the table. Then substituting the given initial conditions to y of 0 and y prime of 0. Y of 0 becomes 1 and y prime of 0 becomes 2. Distributing minus 4 to get s squared Laplace of y minus s minus 2 minus 4s Laplace of y plus 4 plus 5 Laplace of y equal 1 over s squared. Simplifying the constant terms to get s squared Laplace of y minus s plus 2 minus 4s Laplace of y plus 5 Laplace of y equal 1 over s squared. Step 2. We need to solve for the Laplace of y. Keeping the terms involving Laplace of y on the left side of the equation and moving the rest of the terms to the right side to get s squared Laplace of y minus 4s Laplace of y plus 5 Laplace of y equal 1 over s squared plus s minus 2. Taking the common factor Laplace of y to get the other factor as s squared minus 4s plus 5. To isolate the Laplace of y, we divide each term by the factor s squared minus 4s plus 5. Then cancelling the two factors to get Laplace of y equal 1 over s squared bracket x squared minus 4s plus 5 plus s over s squared minus 4s plus 5 minus 2 over s squared minus 4s plus 5. Step 3. Now we manipulate each Laplace transform until it matches the table entries. Let's start with the first function. Find out the similar entries in the table. If we glance the table entries, but we cannot find a similar one to the question form in the table. Since the fraction seems to be complicated, we try to split it into partial fractions. Since the factors of the denominator are both quadratic, we put the linear functions on each numerator with undetermined constants a, b, c, and d. Even though x squared minus 4x plus 5 cannot be factored, we keep it as it is at this moment. If we can factor it, then it is better to do so and split it into more partial fractions as well. Then let's solve for the unknown values a, b, c, and d by making a basic equation. To make a basic equation, we take the common denominator as x squared bracket x squared minus 4s plus 5 for all terms. Once we took the common denominator, then multiplying each term by the common denominator to get the basic equation. Basically, all numerator terms of both sides are called the basic equation, which should be used for solving a, b, c, and d values. We found the basic equation, so let's open the brackets and organize them by like terms. Start with s cubed term, s squared term, s term, and the constant. Once we organize the equation, equating the coefficient of each term, we can see just the constant term 1 on the left side of the equation and 5b on the right side, so they must be equal. Therefore, b must be 1 over fifths. For the other terms, since we don't see any other terms on the left side of the equation, all coefficients must be 0. So a plus c equals 0, b plus d minus 4a equals 0, and 5a minus 4b equals 0. It looks like we need to solve the system of equations to find a, c, and d. We found only b so far, so let's solve the system of equation to find the other unknown values. Since b equaled 1 over fifths, substituting it to 5a minus 4b equals 0 to get a equaled 4 over 25ths. Since we found a equal 4 over 25ths just now, substituting it to a plus c equals 0 to get c equaled negative 4 over 25ths. For d, substituting b equaled 1 over fifths and a equal 4 over 25ths into b plus d minus 4a equals 0 to get d equal 11 over 25ths. We are still working on the first Laplace transform, and we just found partial fractions for that. Since we can see two terms on the numerators, we separate into two fractions. Simplifying the first fraction to get 4 over 25ths times 1 over s plus 1 over fifths times 1 over s squared minus 4 over 25ths times s over s squared minus 4s plus 5 plus 11 over 25ths times 1 over s squared minus 4s plus 5 at this point. For the first two terms, this seems to be simple enough to look up the table. However, The third one and the last one seems to have problems to match the table entries because of the denominators. As we have seen before, we cannot factor the denominator. Let's try to complete a square. Taking half the coefficient of s minus 4 and making square the result to get 4. Adding 4 and subtracting 4 to make the complete square form. Using the complete square formula to get s minus 2 to the square plus 1. Let's go back to the previous slide to continue more work. We rewrite the original expressions using the complete square form. Now, let's match the first Laplace transform in the table. There is 1 over s in the question. We can see it as entry number 5 in the table. Let's go back to the previous slide. We found entry number 5 for the first one, so let's move to the next one. For 1 over s squared form, we can see the entry number 6. For the second one, we found the entry number 6. Let's move to the third one then. Entry number 23 and 24 are similar to the question form. However, number 23 has only constant b on the numerator. The entry 24 is not quite same as the question form, but we choose that one since there is s on the numerator at least. We can somehow to get s plus a on the numerator later. The entry number 24 seems to match the third one, however, it is not quite the same yet. Let's manipulate to match them. A in the table matches minus 2 in the question, so a should be negative 2. B squared in the table matches plus 1 in the question, so b should be 1. As for the numerator, the table shows s plus a, so it should be s minus 2. To have s minus 2 on numerator, we subtract 2 and add 2 to compensate. Since there is an extra plus 2 on the numerator, let's split the fraction by separating the numerator. Then we distribute the coefficient of negative 4 over 25ths into the two fractions to simplify. The first part is matched with number 24 in the table with a equal to negative 2 and b equal to 1. For the second part, it is not the same form as number 24 since there is no s's on the numerator. However, it is the same form as the last one, as you can see. So let's combine the two terms to be 1. Simplifying the two terms to get 3 over 25ths times 1 over bracket s minus 2 to the square plus 1. Let's find out the entry number for this one in the table. For this form, we select number 23 as there is a constant b on the numerator. We found the entry number 23 for the last part. A in the table matches negative 2 in the question, so a should be negative 2. B squared in the table matches plus 1 in the question, so b should be 1 for the two positions. Please keep in mind that we just finished the first part of 3 parts of the Laplace transforms. Let's organize the results so far. For the first part of the Laplace, we found 4 matched entries in the tables as shown. Then we need to move to the other two terms. Since these two terms look familiar, we combine the two together. Same as before, we complete a square for the denominator. If you're not sure about this part, please go back to the previous slide to review. Now, if you take a closer look at the result, it is exactly the same form as the third one of the previous work. So we use the entry number 24 with a equal to negative 2 and b equal 1 for that term. Since we found all entries of Laplace transforms for our question, let's list them all. Please keep in mind that we are still in step 3. The first 4 groups are matched Laplace transforms for the first term. And we just found matched entry 24 for the last 2 terms of the Laplace transforms. Let's move to the last step to solve the question. Step 4. Take the inverse of Laplace transforms to find the original function f of t. Let's start with the first entry, taking the inverse of 1 over s to get 1, so we get 4 over 25 times 1. For the second function, taking the inverse of 1 over s squared to get 1 over 5 times t. For the third function, taking the inverse of the entry number 24 with a equal to negative 2 and b equal 1 to get negative 4 over 25 e to the 2t cosine t. Next, using the entry 23 with a equal to negative 2 and b equal 1 get the inverse as 3 over 25 e to the 2t sine t. Lastly, using the entry number 24 again with a equal to negative 2 and b equal 1 get the inverse as e to the 2t cosine t. As we can see, like terms, simplifying the 2 terms to get f of t. If we take the common factor 1 over 25 out, then the solution becomes f of t equal 1 over 25 bracket 4 plus 5t plus 21 e to the 2t cosine t plus 3 e to the 2t sine t. Finally, we solved the equation. Thank you for watching. See you next time.